which explains for our jurors the general background, and then each group has made a short proposal. Are we waiting for a lead? She was. Okay. But I think we'll make a start, and if I may, we have, let's talk a little bit, get our jurors to say something about themselves, but before they do, we had two distinguished grads from EmTech who are embedded in professional life for now 6 years, is it? 6 years, I think, and really quite senior positions. Eduardo, who's a colleague, and he'll tell you a little bit about himself and his background in a moment. And Al, who's a friend of a great friend, of a founding friend within BuroHappold of Wolf Mangelsdorf, and Al is his kind of descendant and colleague. And I'm going to ask each one of them to very briefly stand up and look at you and say something about their background.
That's it,
start with you.
Have to do that, yeah. Hi Rob, thank you for the invitation, it's my pleasure to be here. Al Fisher, Head of Computational Development at BuroHappold. I've been working at BuroHappold for maybe 11 years now. My background actually is structural engineer, University of Bath. Did civil and architecture engineering there with Chris Williams, who was again sort of interweaved with a lot of the sort of culture of the AA and other practices. Then did my PhD with Chris in complex geometry and solving Navier-Stokes equations and fractal like vortices and really practical things that I've used a lot in industry. So for a long time I was based in, don't laugh too hard. So yeah, I spent a lot of time in our Bath office, which is BuroHappold. We do a lot of lightweight structures and stadium work, and then 3 years ago moved across to London, which is where I now head up computational development and our sort of distributed approach to code development that we have in practice. So, it's my pleasure to be here. Thank you very much.
Okay, well, it's Richard. So I'm Pablo Zamorano, EmTecher. I head the Geometry and Computational Design team at Heatherwick Studio, where we work in bettering projects, around 20 projects live at the moment where we're working on, and we look at any kind of complex parts of projects, but only or mostly related to design with a focus on fabrication. I did EmTech with Camila, I think 2011, I think. My background is an architect. So that's me.
Hi everyone. I guess everyone knows me. But yeah, I'm Camila. I work for Grimshaw Architects in different types of projects, computational design work as well. We're doing different bits and pieces everywhere, like Eden, Baku, Expo 2025, different, big botanical gardens. So we're kind of mixing sort of computational design ecologies and how these things can work in the future. As well, material systems as well.
Hi everybody, I guess you also know me. I'm Eduardo, Rico, one of the directors of Landscape Urbanism here at the AA. I'm civil engineer and graduate from Landscape Urbanism myself. I've worked a number of practices in the past, like such as relational urbanism, but now I'm carrying out a PhD working on sketch captioning and participation methods for urban planning.
Hello everyone, my name is Rick, and this is my partner Cameron, and we're presenting our MSc thesis on robotic nomadism. And we'd like to start out with our ambition and a quick quote which inspired the research. The ambition of this research is to create habitable forms for pastoral nomads which respond to dynamic terrain conditions and nomadic occupation and can be constructed remotely with locally sourced materials. And a bit of the reason we're looking into traditional methods of building and how to incorporate them was inspired by a quote which states, like, our conception of modernity creates its own self-enclosed canons of traditionality, traditions identified as the path is a modernist idea. The same holds true for the concept of vernacular as equated with low technology. In the context where the relation between traditional and modern has a fixed temporal reference, tradition, seen as a settled body of knowledge that can be transferred, uncovered, mastered, and laid claim to, is best reactive and at worst mortuary. And so a bit about nomadism in the Sahel.
So, long-distance mobility between different agroeconomic zones and areas of traditional cross-border movement are deeply rooted in West African history, which has always been characterized by a high degree of mobility. Pastoralism is the main activity in this area, and usually in semi-arid regions of West Africa, because it involves sustainable use of irregular and fragile vegetation and scarce water resources while reinforcing the growth of local communities. Our focus will be on Mali, which has a high percentage of pastoralist inhabitants. Mobility is the most important response to climate adversity. Mobility configurations are highly diversified, and when talking about pastoral society, we can identify three main types of patterns of movement, which actually depend on their interaction with permanent settlements. These patterns are not fixed, as they can transition from one to the other based on resource availability. The climatic conditions in this area are characterized by instability, irregular rainfall patterns, and periods of drought, having an important influence on what dictates the lifestyle of that the people adopt. While pastoralists generally follow a seasonal pattern of movement that goes north to south, their movement varies from one year to another, because in the same pastoral shed or area, the green-up periods vary. They mostly settle between 3 and 6 months and usually do not return to the same places.
And so to begin our research, we looked into tent structures. There are two types of tent structures, tensile and armature, and for this study, we wanted to look more into armature tents because of their potential to take on a compressive load. The benefit of using tent structures is because they have a high degree of customization and mobility, but their thermal responsiveness to desert conditions are not as suitable as, say, a mud or earthen structure. Tensile structures that we wanted to look into include the tents of the Gabra and the Rembil, which include an actively bent grid shell structure, pre-bent members guiding the form, and unbent members to support the form and create more space. Construction in the Sahel region is seen as a practice, not an event. Houses are continually evolving and changing with family structures, and having a high degree of customability is important. And seen in the Mugsum huts, earthen structures are very common, however they take very long to build. For a Mugsum hut, it can take 6 to 8 months and a community to create just one, and it's not suitable for nomadic conditions.
It is very important to look into locally sourced materials, as most of the construction will be in remote sites, and earth is the most available resource. The earth in the area is mostly anti-soils, which means that they are not layered, meaning that the consistency of the soil is constant even at 61 meter depth.
And the available materials we're also considering are date palm leaves and acacia tree roots. Acacia tree roots grow to be a very long length because they reach all the way down to the water table, and current tent structures are created out of acacia tree roots because they have a very high bendability. And we also look into date palm leaves as a substrate in between the grid shell in order to hold a larger amount of weight.
So our material system will be composed, we'll have 3 layers. The first layer will be an elastic grid shell that will act as a structure, and it will define the form. It will be composed of actively bent members. The second layer will be a fiber mesh from date palm leaves, which will ensure structural stability acting as cross-bracing, while also being a formwork for the additional layer. And the last layer will be a thermal layer made of earth, which will ensure thermal comfort.
And in this way, we can maintain the existing construction practices of the nomads while providing a thermal condition that's responsive to the desert. Our workflow works where we consider the available materials and create a two-part system, and from them we conducted experiments on extruded earth and actively bent wooden grid shells. From the extruded earth experiments, we look into manual extrusion as a first approximation, and then move on to robotic experiments, analyzing the constraints computationally before creating a proposal. And with the wooden grid shell experiments, we analyze grid shell structures and how they actively bend before creating a genetic algorithm, which we cross-evaluate with cultural precedents and modes of housing and dwelling in the Sahel before creating a proposal that could perform with a compressive load.
Going into material studies, we started with understanding the capabilities of wood and bending, and relating the bending moment with the breaking point. Also, we studied the curvatures that we achieved and the cross sections that are needed, and we focused on a 15 millimeter diameter dowels, because these are the most prevalent. This is the most prevalent material available, considering roots and branches.
For our initial computational experiments, we did studies on actively bent grid shell shapes, and the reason they don't work the same as a hanging chain model is because over a span to height ratio of 0.3, elastica curves behave quite differently from circular arcs and from a catenary curve. And moreover, when acting in a grid shell, an individual curve doesn't bend exactly as an elastica curve. It bends in a profile that's different in relation to its membering lines. So for our first experiments, we had anchor points that could translate in the XY direction and actuated by having a vertical load pulling up on the grid shell, and then determined its success based on adding a 1 to 3 centimeter thick shell on top of it. And in our material system, we saw initial shell drying and then later adding on load for thermal conductivity. And so to determine our initial pattern with our grid shell studies, none of them with a 4 meter span achieved over 2 meters of height before breaking. But we did notice that triangulation could hold more, did not enclose as much space, but could hold more soil than quadrilateral forms, with exception to a diagrid form, which could hold 3 meters of soil without cross-bracing. And so that was the form we decided to go with for our further computational experiments.
For the intermediate layer, the date palm mesh, we looked into density, and because density is related to fabrication time and also the resistance it needs to take on soil, and we decided to continue with a 50% density because it's a balanced solution. For the third layer, we looked into thermal comfort and considered the thermal resistance and the thermal lag of soil. Both are important when looking at soil, and for the existing climatic conditions, we actually needed around 20 to 30 centimeters of soil thickness, which would which would need like a lot of material and also add a lot of weight to the structure while increasing the fabrication time. So we looked into methods of decreasing the material usage. Adding air gaps would increase the thermal resistance. Increasing the energy flow path within the material will also increase the thermal resistance and the time lag. And cell shading patterns would decrease the amount of solar radiation that hits certain areas, so would allow control. Seeing these methods, we realized that the most efficient way to fabricate it would be to develop them in multiple layers, starting with a flat layer, then adding layers to develop air gaps for thermal resistance, and then having an additional layer for self-shading. So we looked into different ways of extrusions and different types of extruders, and we realized that the compressed air extruder would be the most efficient extrusion process. So we continued with some robotic experiments, and this is our experiment setup using a KUKA robot that was available in school, mounting our extruder on the robot and using a curved or flat base layer on which we would apply the soil. The first experiments showed that the difference in pressure is very important, and the way the material is loaded, not to have air gaps. Also, we realized that having a continuous flow of material is essential, because continuously loading the extruder took a lot of time while the printing process was very fast. And we realized that we do not need such a complex tool. Having them layer vertically, we would only need one axis of movement if we would have a robot that adheres to the surface and moves along its.
And that being said, in addition, all of our materials were mixed by hand and could be extruded with less than 2 bars of pressure. So therefore, having something such as a bike pump could be used in our material system. Although we used an air compressor, we kept our pressure levels low so that it could be applicable to our system. And there were variations in pressure based on material changes in viscosity, but not enough to cause failures typically.
So we tried to understand what pattern would be best suited to respond to solar radiation and shading, and we looked into solar radiation related to depth to take into account the air gaps and their thermal resistance, and also calculated the shading percentage during the most extreme daylight conditions. We've seen that the least favorable condition is having a completely flat surface, and the ones that are oriented to 30 degrees. And we investigated different types of patterns, linear variation and surface variation, and the linear variation was favored because it was more easy to develop and to produce.
And yeah, also we noticed that printing on a curved structure resulted in less slumping than printing on a flat structure. So 3D printing on our actively bent grid shell structures had more surface adhesion than 3D printing on a flat surface.
These patterns had a good thermal performance, and they perform quite similarly. The preferred one is a spiraling pattern that is more dense. And also, one important thing to consider, the vertical pattern had a good performance, but in the same time, seeing the shading on hourly variation, realized that it's very important to have shading when the most amount of solar radiation is present.
And then after that, we looked into using genetic algorithms to develop grid shells which could hold this type of pattern. Our fitness objectives for a grid shell were to minimize the amount of wood poles, to minimize the carrying weight, minimize the amount of joints, which is related to the construction time, minimize the breakage of the actively bent grid structure, both in actuation and when adding a compressive load. And to do that, we calculated the moment, which for a 15 diameter structure was 0.16 kilonewton meters. and created a nodal force, which was the density of Earth times gravity times the thickness of the Earth and times the surface area of the grid shell divided by the number of nodes. And the area calculation that we used for our fitness area, our fourth objective was to maximize standing area. So if you have a grid shell and it doesn't go above like 1 meter, it's not usable, but above 2.5 meters was our usable area calculation. And so the body plan for this was we started with a circle, created our first guiding curve by adjusting the control points, selecting anchor points, and then our third gene was to move the anchor points in. From that we have our first activation, and because a simply just actively bent grid shell structure in a small construction does not create usable space, we raised the grid shell and tilted it at different angles to see what tilt could lead to more enclosed space without sacrificing its ability to hold a compressive load. And from there we added legs for a second actuation, and then created a structure that was like the Gabra, a combination of actively bent, pre-bent, and non-actively bent structures on top of the grid shell. From there we added our 1 centimeter load and saw how it performed. Using our experiment setup, some results, minimizing joints worked in our favor, but we noticed that since most combinations did not function, there were a lot of null values, which was discouraging initially, but the majority of the fittest individuals were in latter generations, showing that our experiment was working, although the standard deviation wasn't necessarily showing it. And from there we saw that having a tilt was preferred in almost all the generations after generation 50, and the fittest individuals were tilted by the most, and we saw a large variation. For our proposal though, the most fit weren't necessarily the preferred because they were our extreme scenarios, and we were looking for a scenario that enclosed space but was also within a certain bound. So we looked at forms on the Pareto front and selected 4 that achieved our objectives at different scales. And then to look in our second, not all huts in African dwellings are just single-family huts though. When a person is living alone, they could have a structure like we just proposed, but to have a larger family, there's a series of enclosed rooms that don't have an open floor plan, where one space leads to the other, and there's a combination of open air places and non-open air places in the kitchen, in a cooking area. And so for our second genetic algorithm, we had the same objectives with different genes, and since it was a larger grid shell, it did not need to be lifted up or tilted. Similar, to enclose different amounts of space, we had different anchor points that were removed, and were moved in at different lengths to create one large open grid shell. And the same with nesting circles, just as the African housing precedent saw. Here we saw a larger variation of movement throughout the genetic algorithm because there were fewer failures with a more simple structure. And again, our most fit were not necessarily the ones that we wanted to propose, but those on the Pareto front created a space that had half open places and enclosed spaces in a way that could be used for African housing with nesting rooms. But
What's the starting geometry for this version?
was this what?
The starting geometry before you run the algorithm?
This is after the algorithm. The starting.
Yes, so what's the starting geometry?
The starting geometry was simply like a grid shell form with a circular plan lifted up, and then different anchor points are removed and moved in at different lengths. And then for further study, we wanted to look into using smaller robots to crawl in the grid shell and extrude Earth, since we didn't need necessarily 6 axis degrees of freedom. 2 were doing just fine. Adjusting pole size in a gradient, although that would work against our construction time since it would add more measuring, and developing a catalog of solutions related to fabrication time and material quantity. Thank you.
I'll start this one. Well, first of all, I guess congratulations, guys, because I think it's a really interesting sort of bit of research for the time that we've had, and I think it's impressive the amount of work that we've done. Like, you know, knowing that you were just 2, and so some of the groups are almost 3 or 4. Couple of questions, let's say. Well, first of all, about the parentheses, how do you always have the misspellings? Because, you know, you're going to publish these, and that's kind of a minor thing, but it's like, it could be a sort of major sort of, you know, thing that you could have. Then a question regarding the fabrication bit of it. So you've tested like robotics, and it's mainly for the third one, because I could see all the rest being sort of, you know, you run the algorithm and you build it. But if you were to send this to Africa and then get the whole thing built, how would the third layer work in that case? Is it like a component that you're sending, or is it like how are you thinking in the fabrication bit of it? You're thinking the robot go there and then you build the whole thing at once, or is it like that you're going to connect pieces together, and if so, how are you going to connect them? If you could just talk a little bit more about that.
Yes. From a fabrication point of view, we are thinking that the robot travels with the nomads, and it can deploy the material circularly around the grid shell on site, and it can develop the first layer within a day, so we will have an inhabitable structure, and the next layers could be developed in the further days to improve thermal comfort.
And like in terms of what we send, simply a plan we send to those in Africa, and they could use routes that they already extract or use in their current tents, and then actively bend those in a grid shell. And so the only thing that would be sent would just be like a plan and a robot.
Yeah. Okay. Because it would be good to kind of illustrate that a little bit better, and so you know you get a bit more. And even if it's an insight, and I know it's an MSc and you're not meant to be doing like any MR sort of work, but you know, this is part of your system, how you want to deliver it, and I think it could be great if you could add that at the end of it, like diagrams.
I'll just add into that, because I think that's a remark that could be really quite beautiful addition to this. It's almost a deployable pack.
Exactly.
Where it's the instructions, actually, what does this look like? This is the kit. This is what I find locally. What am I finding locally? What do I, you know, almost like, you know, not to overuse the sort of IKEA analogy, but the sort of,
exactly.
these are the steps that I need to do.
So the kit parts.
You know, this is the kit parts, this is what I need to source locally. I think that's really good one.
I agree.
So,
again, congratulations. I think it's something nice piece of work. I think the key part is really important as an addition, but I also think you guys need to focus on the sequence. How you actually sequence this process through this key part. You know, when you talk about active grid shells, is it really working as an active grid shell? How are you sourcing that material, and then how are you deploying it on site? And what are the step 1, 2, 3 in order to, you know, raise this thing and get it into the actual shape? The other thing I wasn't so sure about is how you guys were working with the robot. And here moving into kind of more the material side of things. Some of the studies you show for deploying the third material to the second one, we're showing a robot kind of extruding this on a kind of metal, a band metal sheet or something like that.
It was a CNC formed foam, and we also tested it on a date foam mesh. And yes,
So it will be the real.
Yes,
exactly.
that was where I wanted to arrive to, because I think the adherence of that kind of net will be completely different to a flat sheet of material, and that will give you a different kind of set of results. And I think that's how you should kind of push this forward and learn from the material, you know, react to that, and then develop, you know, this kind of system further. Also thinking in the materiality of the third layer, I believe what are the materials you tested?
The materials we tested was similar to the locally found earth type, which is 80% sand and 20% clay with fine sand.
Which mixed manually.
Yes, mixed manually.
And then you try different kind of mixes in order to get
with water content, and we conclusion that around 25% water content is perfect for extrusion.
Great. Yeah, so that's good to hear, because I think this is a really necessary part of the study, you know, in order to get this kind of feasible. The other question I had was on the nomadic side of this. It's more of a kind of fundamental question rather than just go into the detail, but is this supposed to move, or is this supposed to just be deployed, last for a year, and then basically, I don't know.
Yeah, the poles can be used from existing tent structures or found as they currently find them, and then the earth is removed and it stays in place.
It stays in place?
Yes.
And all the kind of the main structure will also remain there?
The poles can be reused and moved on.
Can be reused.
Yeah.
Yeah, you mentioned at the start of the presentation was the routes. So I think there's a sort of different timescales that you could almost sort of map out in terms of I suppose how they're deployed. So I think when you noted in terms of like the temporal nature of actually how does this go from being a kit of parts into an actual assembled object, a building. And then, yeah, I think it'd be good to explore a bit further what happens next in terms of the life cycle beyond that. Because you're plotting those routes, and you alluded to the routes changing, but in terms of the resources that, I mean, I'm trying to imagine, actually there's a question to you, how big is the nomadic community? How many people are moving in groups?
They can grow up to like 200 people,
Right.
and minimum 20, yeah.
Okay, perfect. So
It's a larger community.
right, okay. So I think that'd be interesting as well, to sort of map this to kind of say, well, as part of the community, what is being needing to travel with them? You mentioned the sort of robot. What materials are they having to sort of take with them? What materials are they wanting to sort of rely on sort of accessing locally? So I think that's the sort of question I had. Okay, a more specific one in terms of the sort of, I suppose the sort of construction and typology. So you were considering the sort of tensile tension, more sort of tense style typology versus the sort of active bending, compressive. And I understand from your presentation you urged towards the compressive one because you were needing some sort of thermal mass in terms of to be able to safely. Okay, perfect. What sort of scales were you looking at in terms of variation? The sort of spans you were looking at?
For the single family dwelling, it was a radius of like 3 to 5 meters, so to the maximum 10 meter span, and for the larger dwelling, it could go up to 40 meters in length, but 12 meters across.
Okay. So I think when you were talking about the loading, you were talking about in terms of approximating the dead load of the installation layers.
Mm-hmm.
I think it'd be really good, again, to include, I suppose, on a building of this scale, a level of sort of robustness and resilience cases as well, because this is the sort of thing actually for the working tent, working in building, just literally, how strong are these connections for actually, you talked about breaking through the cycle of the correction sequence, but also just in terms of the daily, pushing, shunting, I don't know, someone butting up against it. So that was my one question. You've got this benefit of this extra mud thermal layer that actually almost produces this extra sort of resilience and sort of robustness to it. And then you just pull that thread out. So I think that'd be something that plays to the strengths of material properties for what they're needed for. So I don't think you've got any necessarily problems there in terms of how your design will always pull that thread out in terms of you're almost using that extra layer for multiple properties and almost celebrating that more directly would be quite good, I think.
I think you have quite a lot of work, I think it's good, but you definitely need, during these, I think it's 10 days, I think it's before, you have to make sure that the initial part of the research where you discuss what you sort of like went to study these existing typologies is a bit more linked to the second bit. It's not too difficult, you just have to be more explicit as to what is it that you are adding to what they already do. Like, do we need more length? I'm sure you have that. This is you didn't tell us.
Yeah.
Oh, look, this is the typical length, and they want more children, so it wouldn't be bad if they have whatever. So then that links to this kit of parts by which the guy sends a photograph of the sticks available through the mobile. I'm sure they have no, I mean, it's likely that there will be some things that they will have that you didn't imagine. And then they receive, oh, do this and do that to obtain that, you know, so you have to build a bit of a narrative through this skill that ties the entirety of the research together. And also go to the last bit, because it seems that you are solving a problem that nobody asked. And I'm sure they have a problem. You didn't get it. And I think also this puts a bit into perspective the role of the technology. I don't actually know if they can actually afford to take the robot with themselves, so they just order it. I don't know. It's just, you just have to imagine a bit how this all works together, putting a diagram, repeat of the booklet. So hang on a second, bam, bam, bam. Otherwise, the background looks a bit more of a sort of like a colorful introduction. So actually, no. So I'm sure you've done it. It's just you didn't show up because you were too focused on the Pareto front, whatever it is. I think if we link why should you use the Pareto against the other ones, because those three guys wanted a bigger kitchen or whatever. It's just that sort of like, I'm sure you've done it, it didn't show up. And the book wants that sort of like stuff every now and then show.
I mean, I guess this is something that could even be deployed as a phone app. You know? It's something because it's easier for them to travel with. For sure, most of them will have a phone. It happens in this you know, countries. They all have an amazing phone. You know, but then they also just decide, you know, this is a scale of thought, and then it runs the calculations. You know, it goes through the iteration. They don't have to focus on that, and they don't need a specialized computer to run that. You know, and tells you, okay, this is what you need. You know, this is how you lay everything on the floor, and then step 1, 2, 3.
It's almost reversing that. It's almost constraining the design process a little bit more. To say almost, I'm at site here. I've got this length of routes.
They have these photographs of Natasha.
I've Drum Board by Foster.
Yes.
That's kind of it, isn't it? Thank you.
Thanks a lot. Thank you.
Hi everyone, I'm Anuradha and this is Elizabeth, and our topic is gradients in recycled composite materials. The ambition is to recycle plastic to use it in a cement-based material as a replacement for sand. The effect of the plastic on structural performance will be examined by using a gradient of plastic content from less to more. As an experimental setup, landfills are selected. A structure will be transformed from on-site plastic producing waste formation and to function as a recycling hub to improve conditions and logistics while optimizing living conditions.
So as you can see here, the most landfills appear in Asia. Moreover, Mumbai is an extreme for landfills. So there are 3 landfills in Mumbai and 250,000 employees. Concrete is a local building material in Mumbai, and since concrete is becoming a non-affordable material, the need of an alternative building material rises. As an alternative building material, we are introducing plastic in concrete as a replacement of sand. Existing research shows no application in architecture because of weaknesses of the material which are implied by the material. We are exploring techniques within our material system to improve material performance as a building material. Okay. We're here. First, examinations start by comparing the replaced with its replacement, so sand with plastic. It is known that plastic is a relatively volatile material under heat. Plastic has a much lower density than sand as well, and this makes our material lightweight. In Paravi, which is our site, It is an informal settlement in Mumbai that recycles the city's waste. We have chosen a site close to dumping grounds that receive 3,000 plastic bottles to establish our recycling hub.
So, solutions from existing local architecture were chosen to adapt to Mumbai's climatic extremes, which are heavy rainfall, extremely high humidity, and low wind speed. So, thin shell roofs help to mitigate rain and improve airflow, and whereas openings on the facade can be manipulated to improve airflow, like ventilation, or to provide indoor shading.
So for material specification, we are using shredding as a method to recycle plastic, specifically PET due to its toughness, besides being readily available on our site. So when we're adding PET to concrete, it now becomes resistant to fire and heat. However, the bonding between PET and cement reduces. Therefore, to improve this behavior, we are choosing extrusion as our fabrication method because it improves uniform mixing and it improves the condition and uniforms the mixing of the material. Up on recycling sand by 20% and 50% introducing PET, the result in concrete shows lower compressive and flexural strength. However, it becomes more ductile. Therefore, we are proposing a material system with a functional gradient between strength and ductility.
It was interesting to find similar examples of graded material from low to high density, for example in a human skull. This informed us that for a shell, more ductile material forms the inner part, whereas the stronger material must be distributed on the surfaces. So for our material experiments, we started with finding out the right flake size and the optimum water-cement ratio to understand the extrudability of the material. To understand the workability of the material was roughly around 30 minutes. And finally, we also tested the buildability of the material composite as a function of the nozzle size. What we observed was that a flat rectangular nozzle permitted lesser pressure, more layering, while also increasing surface area. Initial tests with the extrusion method resulted in a pump mechanism. However, upon introducing PET, more force is needed, and because of that, we opted a lever-based mechanism for the extruder. So here you can see the material performance of our alternative graded material in comparison to plain concrete, and we see the values of material performance approaching towards concrete. However, the constraint observed during extrusion were we started with extruding on a formwork of span to height ratio 2, but we could achieve only up to 3.1. And while extruding different mesh sizes, a range of from 3 centimeters to maximum 6 centimeters was concluded. For our computational design, the mesh sizes were therefore adapted to the wind pressure and sun angle on the global form. For our form finding, the computational process was divided into generating the outer layers first, followed by generating a variation in the mesh size on the inner layers. An optimization process was run based on environmental and structural performance criteria in the end to obtain a mesh shell structure as an output. So our global form was a continuous shell which was analyzed for the stresses. Based on that, force lines were generated uniformly along the V direction because we assumed a simple geometry of a dome, and along the U direction the force lines were distributed on the basis of the stress value. These force lines then acted as a base geometry for obtaining data from the environmental analysis. So the optimization process was directed towards achieving the goals of minimizing solar exposure indoors, for minimizing the deflection on the shell, and for overall minimizing the material use, so minimizing the surface area of the shell. The outcomes exhibit a structural gradient on a material level and an environmental gradient on a geometric level in terms of the scaling of the openings or perforations. So we observed that for an extremely low sun angle, the openings optimized to increase the indoor shading to the maximum, and also deflection reduced in the shell as the algorithm tried to minimize the solar exposure. However, this was not constant for any span of the dome. So basically, to adapt to our fabrication process using an extruder, a reusable formwork logic was used for the construction process. A slice of formwork gradually rotates to extrude in phases over the entire form. So as further steps, we would like to more complex surfaces could be explored using a robotic arm to guide the extruder, because the mix is now optimized for extrusion. And also we would like to analyze the indoor ventilation for wind to understand the effect of these variation in opening sizes on the indoor conditions.
Really interesting. I really like your starting hypothesis. Actually, really interesting. So you talked a little bit about the ability to control the grading of the size of the granules of plastic complex. Can you talk a little bit about how you're actually controlling that? Actually having a sort of hybrid mixture of layering those densities. Was that controlled with different mixes coming from different nozzles, or how might that happen in practical terms if you wanted to vary the density across a given cross section?
So the gradient is across the thickness, and each layer has the same material composition. But the next layer would have more and then more plastic each time. So it's layer by layer, and so every time you add more plastic, the amount of water we add reduces, because plastic has less capacity to absorb water, so it makes the mixture more watery, and so every time that changes. So it is one extruder that goes layer wise.
So that was going to be my last point actually, in terms of, I think it would be good to highlight further the additional benefits of increasing the density of the plastics, because you're actually reducing, one, you've said the water content, which I presume is another precious resource that we want to minimise the water, but also the cement content as well. So actually on the outer surfaces you want a higher ratio of cement in terms of the strength of the material. In the inside you don't necessarily want that same level of density of cement. So those are two really precious commodities, which is cement and water. You want to be reducing those, highlighting that a bit more overtly in the presentation. Would be really valuable, I think. I mean, some other comments I suppose would be the approach you're taking as well with doing the building up of layers. You don't talk anywhere here about reinforcement in the concrete. Is that something you could have a few comments on?
Like we wanted to have one material only varying in its, so as one composite varying in its composition, and not have another material as a reinforcement. So and that is what would, so one material would be more structural, so you don't really need, that was our setup, that we don't really need another material to act as a more structural material. Instead, the geometry would be optimized to handle the tension.
Right.
Yeah. So that's also why, as a starting step, we took a dome to yeah.
And again, I think really, if you've considered it, which sounds like you've considered it, make sure that's coming out really, really clearly. Because the first thing, I think even if you kind of have global and local effects as well. So globally, you have a structural typology that is primarily going to be working in compression. Again, you might always have, I'm looking at your samples there, and obviously even just locally, that's where you're quite fragile, because even if globally it's working in compression, you're always going to have to be resistant to some local point loads or robustness again, which is where some reinforcement is required. Now, that doesn't necessarily need to be an entire mesh reinforcement, but yeah, considering that will be really important for this sort of scale in terms of its practicalities.
Okay.
Just for environmental condition, actually, in terms of the rain, for instance, is it waterproof? Because I see there all the examples that you have, or proposals, are all with, there is this compressive sort of shell, and then, there's not kind of anything else. So is it, if you're going to have people in there, at some point it's going to rain, or, how you guys thought about this?
So we based on the, we are selecting only a certain portion of the global geometry to have these perforations, and based on that the usable area reduces by a percentage, but that is what is our 120 square meters. So the periphery would would have rains, but it could be drained out. Yeah. So the top part is solid, but it also has a gradient, but it doesn't have perforation, so it essentially just has one gradient, which is a material gradient. But the openings do not. Yeah.
Okay.
And what about heat? How does it react to kind of extreme heat? Because it's plastic, I imagine it could
be like this.
It could affect somehow
glass house effect.
Properties.
So its melting point is around 90 degrees Celsius, and the ambient temperature there is 34 degrees Celsius. But it's because of it being inside concrete and concrete being resistant to heat, we are assuming that, and even if the surface temperature is higher by a certain percentage.
Because that's quite interesting in terms of the gradient you guys working between the two materials. Because you could, for instance, like now we're working on big sort of ETFE groups for different projects, including Heathrow actually, and the level of freighting that you need is quite important to get the level of comfort that you need, because it's different to treat for plants and for human beings, right? So that could be a really interesting point that you guys could make. You change this ratio, it works structurally, but also it could work environmentally. So that ingredient, I would definitely work it out in terms of how you work out opacity in order for you to make a really comfort space that you nice to be in.
Can you go one next? If I understood, so you do it by layers. So the more you go up, the more plasticky it gets, because you need less.
The inner layer.
The inner you go, it's more plastic, and the surface layers are more concrete.
Just concrete, pure concrete.
So when you mean by layers, it's towards the inside.
It's
or towards up.
Up.
So more up is more plasticky, because you need less strength and it's lighter.
More
right?
Middle you need.
Sorry. Is the cross?
I think that's where the analogy from the bone comes from.
Well, that's what I suggested. At the moment you're tackling just the structural bit of it, but it would be great if the system could work environmentally as well.
I was also thinking in the opportunity and using the plastic not only as a granular thing, but you could also extrude it, using the same machines that you were using for this, and maybe think of the plastic as a fiber. So if you want to reinforce, tension, maybe you can play around with the material in a different way and add more to your system in that way. Also, I think as it's done now, it may also work as a brick. Because it's very self-contained, and then maybe you are adding more possibilities to your material system by making a module, a very kind of model that you can repeat and make it work as a compression system, a pure compression system, rather than trying to force it into something that's needing, to work with tension as well, but it is fighting against the properties of the material. So I think both approaches are ways forward, I think, for this.
Yeah, and again, the same as last group's going to so sequence of how you guys are thinking to fabricate these is quite important, and we'll definitely up that for clarity of how this will work when it's built.
Yeah, if this is all extruded in situ, then you say, how does that actually work
Exactly,
in terms of the, is there temporary formwork, or is there something that is formwork then becomes permanent, or some options there?
I think this is go one more slide. So I don't know if I missed. I can't remember if you made it clear. I think you should just be a bit more playful, or a bit more explicit as to how different PET mixes fabricates different final outcomes. Because otherwise it becomes a solution and it works and you have to trust it, but you didn't really play with it. The hammers are more plasticky how or the smaller ones are for plasticky. It does seem that you're not playing with it. It's just a given.
Thinking they're architectural properties. How does it look when it's more when it's got more plastic? So it's more translucent.
Simply smaller.
Yeah, that's the thing about the gradient.
It just becomes a solution that is just taken for granted, and then you do something else. So I think you should speculate it.
And there actually can be different mixes where you say, actually this is the mix that is optimized for its compressive capabilities, so that's the primary system. Well, actually these are some infill mixes which are incredibly translucent. Then you're kind of playing with that beautiful. That'd be really cool. Yeah.
Okay, so I'm Brittany and this is Alina, and we're doing our MSc presentation on intelligent territory. This dissertation aims to achieve an ecological design system for border conditions susceptible to desertification and rising temperatures.
So the goal is to design a habitable infrastructure that can collect water and provide shade in order to lower temperatures in Nicosia, Cyprus.
So ultimately what we want to do is we want to find a system that will store, collect, and distribute water that will adapt to both urban and rural conditions for seasonal conditions over the next 50 years.
So 57% of Cyprus forecasted to become a desert in by 2050, but territory that divides the whole island and controlled by UN absorbed with the increase in biodiversity due to occupation of the people. So you can see the conditions of the site now. This is the city condition of Nicosia.
And along the UN border zone, there's a different porosity, and it's also dynamic in how the depth and how it cuts through both the city and the rural areas, which you can start to see here. So there's no defined border, it's more of spatial conditions.
But even now, the temperature in the city exceeds like 44 degrees, and in 10 years it's going to be 50 degrees, and you can see the pattern of the people that everybody just walking along the shade.
Yes.
Or you can see nobody.
Yeah. So in order to achieve our goal, we looked at shading, vegetation, cooling, and adiabatic principles to move on with our
And we were also looking at the precedents, how we can combine to achieve our system that can connect light, wet structures and water catchment techniques, and develop the material and the existing material meshes. So we looked at the fog harvesting techniques, we looked at the state-of-art the mesh that collect water and lightweight structure that can be resistant to the high temperature in the future. So, and our research question is, can a system be developed to control rising temperature using lightweight structures while maintaining a continuous territory in Cyprus? And our basically design strategy is collect water, store, distribute, and shade. So our experimental setup, our goal is to reduce evaporation, increase shadow, and increase biodiversity along the border that has an urban condition and rural condition. And to use that in rural, we can use the topography and vegetation, and we want to test what kind of infrastructure can be developed to achieve the goals. So we looked at the two patches, rural and urban.
And ultimately what we want to do with the urban is reduce evaporation and increase shadow. So with the urban shading intervention, it's responding to desertification in Nicosia by incorporating solar and wind principles to provide a solution to counter extreme climatic conditions. The Nicosia is located in the heart of Cyprus, which is prone for desertification, and because of that we selected 4 patches that have exceeded the environmental critical threshold, which have the highest failure based off of human comfort. So these four plazas will no longer be able to accommodate people because the temperatures are exceeding 44 plus. So by analyzing the relationship between the plaza and the street, we start to assess the range in static pressure, which is very low, air movement, which is also very low, and high solar exposure, which ultimately what we want to do is we want to reduce the heat absorption by reducing direct sunlight and utilizing a shading system that would reduce or increase reflectivity, increase shadow, and reduce heating conditions. So we've developed an urban component that starts to use the principles of the chimney stack effect to ultimately extract out stagnant hot air to improve cooling. And by doing so, we've included the angle, the height, and the diameter to inform this geometry. And so each one of these are specific to to the plaza, which is responding directly to solar and wind conditions per. And out of the 4 plazas, these are the fittest criteria, which is responding to the highest environmental demand, if it needs more sun or if it needs greater shadow. The placement logic is based off of targeting the highest sun value and placing this shading device there to increase shadow and reduce ambient temperature. So what we've done is we've extracted the geometric parameters out of this tower by testing its relationship to the ground, its porosity, and also the depth to increase wind flow and increase static pressure. And like I said, these geometries are utilizing the chimney stack effect. So we're testing that based off of the total amount of shade projected onto the ground. And in the summer, which is the most extreme, we're able to increase the shadow on the ground by 47%. So this is also contributing to our ambition to improve the outdoor climate. And ultimately what we do now is we want to reflect on the performance of the shading system based off of our environmental criteria. So by placing in the shading and the urban component, we see that we're able to increase the velocity, and we're also able to increase the air movement based off of the perforation in the actual canopy system, which was also determined based off of a range of angles. And because of this, we're able to extract more hot air out of the stagnant plazas. And again, in parallel, we test the shading cast on the ground. And so in the winter, we're able to increase shadow by 46%, whereas in summer, because of the angle of the sun, we're able to nearly provide 100% more shading. And so based on the pattern and the behavior of this system, we determined we want to maximize the shade and minimize the area or the surface material used. So we consider the density, porosity, and wind flow based on this reconfigurable system. So by using this system, we're able to minimize the density of the surface, and we're also able to increase the reconfigurability based off of the seasonal conditions. And this is how these two systems come back into our original ambition to lower temperature.
And so moving to rural conditions. So for rural, the goal is to reduce evaporation, increase shadow, and increase biodiversity. And in order to do this, we analyze the topographical condition, the wind precipitation, and solar analysis. And our goal for infrastructure is to maximize the surface exposed to the prevalent wind. So the design strategy is to collect water. So basically, we test in 2 patches that described by high and low altitude, as well as the distance from the sea that is differentiated in the humidity level. So what should be the geometry for both of the patches? And so based on the data in Cyprus, we can collect about 0.6 cubic meter per square meter of a mesh. So then we look at how to store it and how to distribute the water later. So, okay. So for the high innovation, where we can collect more water due to all of the conditions, we were testing which form is better, and the principles is the width and the height of the form, and the shape from 4 to 6 side polygon. And so it's resulted that the best form is we can collect about 2.5 million liters per year when we have 3,000 square meters, and the height of the tower is 42 meters. For the lower patch, it's more important to provide the shade system. So in addition to the previous one, the angle of the form is important. So, yeah. And so to test afterwards how on the local scale 2 surfaces can work, because due to the flat surface, it creates the blockage effect that reduces the amount of water that we can collect. And when we have the 90 degrees angle between surfaces, it increases the pressure on the mesh, and there's more water can come through. So after we collected water, we were trying to find the shortest path using the topography and the principles of gravity of water. How to find the shortest path to decrease evaporation and water loss. Okay, in order to provide the shade, we're testing the system of depth and the width of a channel. How can we, which form is the best? And to compare the analysis of existing land and the land that we manipulated, we've evaluated that we can collect in this form more water due to the runoff. Okay, and then in order to increase biodiversity, we were analyzing the existing land on the shadow range that will create the different site conditions for the planting, and it's evaluating into shaded moist condition that provide the condition for land cover, like lavender, the shaded dry condition that is suitable for shrubs, the sunny dry areas where olive trees and carrot trees can be planted, and the sunny moist conditions where can be a combination of shrubs and the land cover. So as a evaluation, the water demand is about 1 million cubic meters. And the question is how many actually towers needed to build in order to achieve it. Is 465 towers. During this project, we have a question that we want to discuss with you. It's how do we integrate the design system in political and social bodies, which has various topographical conditions? How do we ultimately use these territories, and how can we adapt existing fabric for the future?
ones like that. So both of the places are quite close to each other, right? In terms of the urban and the rural. Yeah. Why one of them needs water collection, the other one doesn't, or why people in the rural one need the water and the other ones apparently don't, or are these water collectors as well, the urban ones?
Well, ultimately, what the rule is doing is it's producing the water, and then over a series of time and the season, it will infiltrate to the urban. And so within the urban, with further research, we can start to show the principles of evaporative cooling. So by increasing the water and pulling it in, we can lower the climate, which is responding to the heat island effect. But ultimately, the production is coming from the highest elevation, and using gravity, we're pulling it to the lower elevations.
It's quite an ambitious system, isn't it?
I have a specific request, maybe. The intervention that you're making in the courtyards, there's almost two parts to that, isn't there? There's a sort of the roof, the sort of shading part to sort of mitigate the direct sunlight, and there's a sort of solar chimney to then sort of
increase.
Yeah. I think it'd be, in order to understand the effects of both of those interventions, I think it'd be useful to have, rather than just both of them compared with the original state, separate that out. So I think that would make it much easier to understand the effects of those. So I'll recommend that really in terms of your analysis. That would be much more compelling to say, this is the original state, we've now introduced this roof, that's the effect that has, now we're introducing our solar chimney. So you can see the effect of the two.
And also design starting point, things that like it seems that all of a sudden we have these chimneys already sort of out of the blue, and then it's tested. So
exactly.
That is, yeah. So how are we really thinking on it? And then thinking of this as a result of the problematic that you guys have set up, or the sites has, basically.
Yeah, I think you can use the elements we have to respond to that question. Well, you have to, I think you just have to look at what you've done, because, for instance, in the water one, I was thinking about the same thing. So why are you placing them in those points in the first place? But then after you started explaining how this thing worked and gathering water and how the water was traveling down, even finding the nearest or the quickest path to reach the mainstream, I was like, well, the third one looks a bit odd. It goes kind of straight down and then to the side, rather than so it's obviously it's
a bit forced.
Yeah, well, it looks like, but if you are making an intervention, then obviously you can shape it the way you want,
right?
And then run it again, and say, okay, well, is now the closest path. But after you show what you did with the kind of the vegetation and the ecological side of things, I think it makes sense. Because you are generating different qualities of the space. It's more of which one comes first, but you can explain it through, planting these chimneys, these flutes, and say, okay, well, we organize them in a way that they will potentially generate this type of space, or this quality of the space, and in particular in the shading one, it's all about the quality of the space, So where you actually need to have shade, where you can have more openness, where you want the people to walk, where you want the people to stay, where you don't want people.
And that could be a really nice adaptive system too, because you could, get a study of the path of, the circulation of people in the specific areas between the buildings, and then when you map all those out, you get all the data into one sort of algorithm which will tell you, okay, so that roof needs shades in here because you have all this building, people are situated that way, and maybe, for instance, like, why not the towers could become grid towers maybe, or, like if you use a very kind of a lightweight tensile structure or something, and then kind of cover it with some green that you could use also for, humidity, and then you could incorporate the water thing as well into that city piece. These sort of different variables that you could add more like in spatial conditions sort of point of view.
I think you should take those comments and definitely look back at this map and the map of the entire area, because in a way you glance very quickly over the qualities of this space, You put a movie, but you don't really sit down and tell us what's happening. Like it's a bit difficult to justify the funnel's own capacity to just collect water. There are other mechanisms to achieve. You have check dams and ways that are very cheap to encourage infiltration and whatever. But for some reason, there may be a reason to create those little pockets with higher amount of vegetation, shading, linked to what's happening there already. But we just don't see it. We haven't seen at all. We said these are the paths that the shepherds go with the sheep, and actually they need a place to put the sheep, but this can be linked to that, and that's why we put it here, and there. And you may as well just do it first and then reflect upon what are they producing, and then go back and say, actually, out of the rural areas, this and this is where actually is likely to be used for this, and in the urban areas, now that we think about it, this and this are the place we should be looking at to put those. But the plan doesn't have a legend. It's like a blank plan.
Almost imagine it's a sort of a phasing as well. I'm saying these are the areas that we're going to sort of throw out in terms of this is the primary place to regenerate. Once you've established that, you've almost created a new use for that space, and then these are those territories. I mean, treating almost as a phasing.
Exactly. It's a quite interesting sort of piece of research anyway, and you have lots of great results, but you need to direct it a bit more. Like you say, well, the computer will give you a result, but now it's you guys. I mean, it's your head, the one that is to go in that project and say, look, I mean, this is the way I'm going to do this because like this is what I want to solve, or they can explain it in more like a tangible way. In that sense, because at the moment it looks really like a computational sort of thing. So if the robot will be kind of making things for these little people that live somewhere there in the air, like it's that sort of thing.
Okay. I think that's fine. Is it a matter of understanding what comes first?
Yeah. I guess it's explaining
is it the fluid or is it the shading devices? Which one informs which?
Exactly.
Or,
just explaining it a bit more diagrams, real life versus what we're designing. But right.
And then maybe just hinting what's next, because obviously this is all about geometry and performance in a way, and regeneration or regeneration, but I really want to see the material of this, what's the materiality of this, and of course this question is maybe too much. But just kind of,
but it could be a sort of hint of what.
Possibilities. You just think in a few scenarios. This is an image or I don't know.
Dropping a bit more of an understanding of what do people use those areas for to see if those funnels get a new use once you. Even if you put it as further study, like try to understand if they use certain types of structures and that, I'm sure they have problems or whatever. Like, at the end of the day, you need to add a bit more of specificity to the funnels because otherwise it's difficult to digest. And I'm sure you will do it, and it will really help if you do that. And then put whatever you cannot do to the further study.
Well, it's also quite nice that you have the output of one algorithm as the input of the next one.
Yes.
So that's like working out in different scales. That's a very interesting thing, I guess.
Good.
So we'll start this presentation by showing you guys a video of our trip that we took to Almeria in Spain. So this is a land that is mostly occupied by greenhouses. As you can see, vast expanses of greenhouses. And there's their major produce is all their crops and farms. So over there we analyzed the sites and we had a look at the conditions, and there are things like pollution and many issues that we will get into later on. Yeah. And my name is Tim, and I'm MSc, and this is my colleagues James and Rita from Denmark.
Okay, so first we're going to start with our issue and context. So we started with, I think it worked. Yeah, okay. So our issue is the certification, and our context, as you can see from the video, is Almeria. Almeria is located in the south of Spain, and what we found interesting about this area is how they tackled the certification with many agricultural methods, which include the greenhouses, and they make this land productive. So As you can see, there are 36,000 acres of greenhouses in the area. Okay, so first we started with the analysis of the area. As you can see from the topography, first we have the mountainous area, we also have sloped areas and planar areas. Then we went into our roads map. So as you can see, the main road is located in the planar area, and then we have numerous secondary roads that connect to the other constructions around the land. And then we have our formal constructions. As you can see, most of the buildings are located close to the main road and also the planar areas, and then we have small houses around the rest of the land. And most important, hydrology. As you can see, all those little dots are artificial ponds that are used for the irrigation systems of the greenhouses. And then we can see that we have numerous natural rivers coming from the mountainous areas. Okay, so Almeria is a result from the certification, and we found three main issues in the area, which are water exploitation, plastic pollution, and greenhouse inefficiencies.
In terms of water exploitation, obviously horticulture industry is really water intensive usage, and also it imposes high stress on the local fresh water resources. And as a consequence, the underground seawater start penetrating to the local freshwater aquifer, which results in the water contamination. And then in terms of plastic, the local horticulture industry produced 30,000 tons of plastic annually. And you can see the majority of the plastic is either burned, landfilled, or dumped in the ocean, and only a small portion are recycled. And to give you a sense of scale, we compared the area covered by plastic to the metropolitan area of London to show the extent of the plastic usage in the local area. Then, in order to analyze the inefficiency, specifically overheating problem of the greenhouse, we studied the existing type of greenhouse. And you can see the general trend of improvement of the greenhouse is to have less structural components inside the greenhouse and the higher ceiling to improve the ventilation. And in terms of a morphological feature which directly affect the efficiency of the greenhouse, so we identified the orientation and the different form of a roof, and also the ceiling height of the greenhouse. So higher ceiling height will have a higher thermal inertia and better ventilation, but at the same time, it also requires a higher structural stability demand, also higher energy consumption.
Okay, so then we did an analysis and research of the 6 main crops in the area. So we overlaid and compared their climatic needs and also some economic information. Then we also did a research of the climate in Almeria so that we could understand their fluctuations throughout the year. And then we overlaid both of them in one diagram so that we could understand that there's a need for a high adaptive system if we want to be able to do all those crops in around the year.
So on to the next parameter, which is the wind. It's a very special circumstance over there where we have predominantly eastern and westerly winds. So as you can see from yearly as well as daily, we have not so fluctuated but between just the two directions. So that type of parameter we want to potentially utilize to harness the wind for its power. So to summarize, we have the water overexploitation, the plastic pollution, as well as the sorry, I need my glasses. As well as the greenhouse inefficiencies. So each of those has solutions that we want to utilize. For example, greenhouse inefficiencies, we want to improve the chimney effect as well as reduce microclimate fluctuations. So therefore we need to adapt a larger volume and height, but then at the same time it requires a larger wind load. And then we get into potentially using morphology to adapt to the changing winds, as well as various other parameters we'll get into later on to form a holistic wind adaptive hydrothermal farm system.
And then move on to the design. We start the design by analyzing the existing precedent. The first precedent we're looking at is the Davis Alpine house in the Kew Garden. In this case, we're looking at how how an architect used underground labyrinths to cool down the incoming air as a passive cooling strategy. And then the second example we're looking at is the desalination techniques in order to use seawater to offer an alternative water resource for the local agriculture industry. So in this case, we want to use a solar distillation, which use sun to heat the water and then re-evaporate and collect it.
So the two aforementioned systems, we also want to adapt it and integrate it into a single system where we can utilize the water from the desalination plant in order to use as hydrothermal mass to also heat and cool for our labyrinth system. And now we move on to the sectional design. This design is divided into two parts. On the windward direction, we want to minimize the positive pressure. And on the leeward side, we want to maximize the natural ventilation. So this is devised from the prairie dog ventilation system, where they dug holes in certain shapes at different heights and geometry to maximize the drag and negative pressure in order to create its own natural ventilation system. So after that, we ran a series of tests using different direction leaning as well as heights. We found first it needs to be a leeward leaning direction to maximize negative pressure, as well as having a minimum amount of height, as well as we tried more advanced curvature variations to find the most optimal shape, as you can see, that can evenly distribute this type of ventilation system. So once we have the adapted most optimal section, we move on to the 3D design, and we devised a plan to have 4 farms arranged together with a desalination plant in the middle. And this is also utilized with GA genetic algorithm for us to further design with the different 3D forms. So as we run through a series of genetic algorithm experiments, we try to maximize the volume to plastic reuse ratio. We try to maximize the packing efficiency, as well as we try to minimize the shadow area. So these are the non-CFD parameters we try to optimize. So after that is done, we take all of our units and we plot it onto our Pareto front, to plot onto our objective space. So as you can see from the general graph, we have a huge amount of data. But so to incorporate our bias, we have an even weighted value of domain for each objective that we chose, and everything outside of that box we eliminate. So within the box, there's still quite considerable amounts and a lot of converged data. So what we do is we make them into clusters, and for each cluster we elected a representative so that we can reduce the amount we can further use for CFD analysis. So out of the 18 individuals, representatives, we ran through the CFD with the same objectives, but this time in 3D. To also maximize the negative pressure, but minimize the positive pressure. And then we selected the most optimal summative value.
So after the genetic algorithm, we also developed the labyrinth cooling system. So here we are running the CFD heat exchange to evaluate the cooling and heating capacity of our passive cooling system. So we run the analysis annually, and we found that our system are able to achieve a cooling capacity by 2.8 degrees and 3.9 degrees of heating capacity.
And then after that, we also went through a ventilation performance analysis to basically calculate the air exchange. The air exchange calculation can be done through the total exhaust divided by the volume of the room. And we get 0.236 rooms per minute. And our research shows that a standard greenhouse requires the air exchange to 1 room per minute. So our results only give us 0.2, so actually we are still lacking by quite a lot. And as we even increase the wind speed to something a little bit more unreasonable, it is still not able to achieve the recommended air exchange. So that's something we have to get back to and potentially increase the ventilation amount as well as the size of the holes.
Okay, so now we go into our material systems and fabrication. So first we look into the precedence of pneumatic structures, and we decided that we were going to focus on membranes, erbeams, and reactive skids. After that, we also did experiment approaches. As you can see, there are many fabrication approaches, and we did many physical experiments, but the one that was the one that had the best result was the air beams. So then our biomimetic concept is the stoma, which is the way that the cells in the plants extract the oxygen. So in the first experiment, we did 2 pre-shaped beams with varying pressure. In the second experiment, we attach a third beam inside of those 2 beams so that we can create openings for the ventilation. In the third experiment, achieving digitally designed morphology with the structural beams. And in the fourth experiment, we attached a surface membrane to the beams. So the last observation was that the planar surface produces wrinkling during actuation, and the surface rationalization strategy needs to be utilized.
And in terms of the structural performance, we are testing different air beam arrangement on the initial surface. So the evaluation criteria, we're using the structural performance as well as material usage and the complexity of the joint. So in the end, we choose the surface adapted approach. This approach will also have the least amount of length change on the air beam during the actuation. And because of the 3D double curvature form has to be fabricated through a flat sheet material with the width limitation. So we rationalize our surface by testing different patterns. And the method we're using here is mesh relaxation with planarized force applied. So in the end, we compare different results and saying the triangulation pattern will be most accurate form from the original form. That's the one we're going for.
And then we went into the material properties. As you can see, we analyzed different types of materials, but we ended up choosing ETFE due to their high durability and also their high light transmittance. And now, this is a timeline of the fabrication of the structure. So right now, we are located after the last dashed line. So first, we really want to address the issue of the job opportunities in the area. So we would like to put a fabrication method there, where we would ask the material from Barcelona or Madrid to be taken into the area. So then we would go into cutting the material with a CNC machine, then to weld it with a welder machine for UTFE with heat sealing method. Then we would transport it to the land, where in the land we would already do the excavations and the construction of the labyrinth and the foundation, where we can attach the components, and each one of the components would have one air compressor with variable bulbs, so that we can redirect the air where it's needed.
So now we move on to the system proposal and evaluation. So now you can see the system integrated holistically. The center is the desalination plant, of which the water that is taken from the oceans is going to be desalinated, but at the same time, that water will be utilized for heating and cooling for the labyrinth, as you see. As the air intakes from the sides, it goes into the labyrinth, gets cooled/heated, and then it moves through to the circumference of each farm in order to be to warm up or cool down the farms, and later on exhausted by natural ventilation. And then in section, you can see more clearly how the desalination works by evaporating the water and gathering onto the side of the plastic, in which it drips down into the freshwater channel, and that water is later collected, and it can be used directly to use as for the terrace farms. And so to summarize the adaptation systems we have, for example, we have pepper over here, which has an ideal temperature range, of which when we go above that temperature range, the labyrinth isn't used for cooling, and then when it's below, it's used for heating. And we also have the ventilation control, which is able to control the magnitude of this effect, of which we try to apply. Wind adaptation, as we discussed, will be adapted according to wind conditions. And finally, a humidity adaptation as well. We want to make sure that when we need to dehumidify, the ventilation opens. But at the same time, when we want to humidify, we can just open the chamber directly to the desalination plant, so that the humid desalinated water can just enter directly through the air and into that system. So here you can just see how the actuation process works and how it goes from one wind adapted direction to the other, and also how the individual ventilation holes can open and close. Oops. Go back. Yeah. So just using tomato as a prop example, the typical process takes about 150 days per cycle for tomato to be produced. But as our research shows that under ideal conditions, it can be produced 41 days less. So what that means is if we do a rough calculation for 3 years, the typical system in Almeria produces 2,000 to 150,000 tons of tomatoes. So just by purely shortening that process, we can also yield 2,900,000 tons of tomatoes instead. And to summarize the evaluation of the ambitions that we set out at the beginning, the greenhouse inefficiencies, we are able to harness the wind and thermal energy and reduce temperature regulating cost, and there's a net gain in annual produce. Though we haven't addressed the energy consumption of the pressurized air beams, which will also take up as the cost. In terms of water overexploitation, there will be a net positive water gain. In terms of plastic pollution, this is something that we address a little bit less because the plastic usage is reduced by geometric intervention. However, it's still a plastic heavy project, and potentially we should address some more things such as recycling systems that can be incorporated later on to this project.
And for the MR ambition, what we haven't touched upon in the MSc phase is how does the greenhouse aggregate together and collectively behave, and also how does the water system interconnected and form a global scale hydrological infrastructure. So those two will potentially form a productive landscape design in our MARC phase.
And also we want to look into the human needs in the area due to the hard working in the agricultural area. We want to propose housing units for those workers, and we would like also to propose the fabrication logic of pneumatic formwork for the settlement.
That's our presentation. Thank you.
Really good piece of work here. This is really incredible. I think really good presentation. I think it was very clear, very thorough. I think you were able to start from a restrained series of questions, and you managed to actually respond to them.
Not always.
Yeah, I think it's a really good work here. Some of my questions have been answered, or at least exposed, but not answered. So energy consumption is what you one.
Yes.
And then how you address the material, the plastic. So I think those are the biggest questions that are still kind of open. On the material side of things, I think it's maybe thinking in what's the lifespan currently there. You know, how often do they have to change the plastic on their sheds at the moment? You know, you can start from there and think, well, so how long is going to last this? You know, how often they will have to change this, and then maybe thinking addressing the kind of enclosure and the inflatable bins maybe in a different way. You know, because you talk about using ETFE, but doesn't mean that you have to use ETFE for the bins necessarily. Maybe that may open a different way of controlling them, because obviously to make this thing adaptable, even though it's amazingly beautiful to think in these structures moving all the time, reacting to the wind, there may be an efficient way to make it happen. That doesn't consume
like a non-pneumatic.
all what you're saving in terms of energy on the other side. What also will be good to see is kind of the zoom out in scale again at the end, and see what's the impact of this system once applied to the whole site in Almeria. You know, as you start with this very kind of zoom out picture, an amazing image of the site, right, where you see how incredibly dense this thing is in terms of, you know, the construction of plastic, which is super scary.
Yeah.
Maybe thinking in how does it look now after you apply the system, you know, and how this is kind of giving back to the land.
Also in terms of, I guess, more for you guys, the like the architecture of each of them. I mean, I deal daily with, 50 meters high domes and working closely with engineers. I don't know, like, it would be good to kind of try to push this a little bit further and then see, well, is it these air beams, do they work? Like in terms of, like structural terms, maybe run some air analysis and then see, because believe me, it is not easy. And so, like if we say that the whole cover is ETFE as well, ETFE is not going to have like 100 meters span, sort of one piece thing. So I guess it's better if we start thinking about that now, and if for the MSc we can have a hint of how this will work, that would be as well a very good input, I guess, for the research. Also considering that, like inflatable structures, because we say that this is a high pressure system, isn't it? So then you inflate the beams and then they stay as they are. So we say that the height is going to be 15 meters and then the span is going to be
110 meters.
Yes, so it's quite good for an air beam, right? Like I'll put an eye on that and then see how can we, because I don't want to close the door for it, because of course it's a research, it's an academic sort of exercise which I find amazing, and if there is a solution, well, why not? Let's try it. But let's try to make it, even if it needs to be combined with a little bit of structure, secondary structure, sort of language structure. But trying to be a bit more realistic for the with 2018 or 2000. So but overall, just I think Science Partners is great research and congratulations.
I really enjoyed the presentation as well. It was brilliant. I mean, even just the slide we've got here, a bit flat in places. That if you're dealing with ETFE, then you're gonna deal with, and a lot of your analysis was talking about how it interacts with the wind. You'll get local effects where you might end up sort of flutter or fluid structure interaction, and the thing actually sort of not being stable under those wind pressures. So I think that's a really good point. I think there's the overall span, and then there's the local geometry. I think, and again, it's you've got to push the boundaries. You've got to be challenging. So I want to shut this down, but just think that you've addressed it.
And also, I guess you'll be impressed when you start, like especially for you guys in VMR, when you start looking at the building a bit closer, the amount of MEP areas that you're going to get because of the whole ventilation sort of thing. But you'll be really amazed because like every time when we deal with engineers and that, it's like, no, well, for that dome, well, it's like 500 square meters on each side of the dome. So you kidding? It's really, really big, and labyrinths are a really good option for it. But you really need to address that issue too, because inside the domes you're going to need some ventilation, massive machines that you really don't imagine how big they are. And also, big important thing is access to the roof. So whenever you have these big enclosures, you need access to the roof. I mean, I'm a bit too specific here, but like I thought this is good to give you a hint of how the thing working really well.
Sorry, and again, you sort of nodded to it. I think it is worth just making sure you got that clear. The narrative, the audio of your analyses and how you tell the whole story was really, really powerful. But you were considering the sort of environmental wind effects on a localized dome. You then, obviously, I thought it was quite impressive actually what you were doing, sort of minimise the computational intensive CFD work by those and then visiting them as a cluster. Now we're sort of seeing one of those clusters then as part of a wider array. I think it's worth really putting together those effects of those individual surroundings on the individual elements. Because actually some of the wind effects you were showing on some of your models are actually being very closely affected by the surrounding buildings. Now, I think obviously your whole project celebrates the fact that you can be slightly adaptive. So I think it could be again something that in terms of talking about the phasing, this is how the building needs to interact when it's on its own. This is how it's going to have to interact when there's actually some later phasing coming in. That's a standard approach that we would have in terms of generally designing the building, designing it for its isolated case, but actually having a nod to knowing, well, actually we've got some future developments here that may or may not happen. making sure that your building works for the now, but also will always work for the future as well. So I think that would be good, especially with your theme of this expanding out, you could pull that out as well.
You've really done a very good work. I think you're in a position where you can do whatever you want. It's not a this guy to do whatever. No, you didn't forget. You do whatever the hell you want. I mean, I can see two paths in terms of technology. One would be more the heroics of trying to solve 100 meter span beam, whatever the hell, sort of like Foster kind of like we're gonna make it. You have a huge labyrinth, DMNE problems, which is a bloody nightmare. So technically, it's a heroic task that I think you can actually deal with it. The other one would be more into a tactical strategy where, I was thinking fourth slide where the cushions of the pillows of the TFE have the water, what does this mean? The water, inside the silk, which is, never done it. It's against the sort of like heroics of we can sort of be big building and actually these guys can do it, right? But if you come up with a pillow, even if it's a small one, that you can do this thing in a 10 by 10 meter, whatever, that just does the job.
Like mini systems.
You
make a mini system,
somewhere
Like it's decentralized.
And it's not heroic, it's not, it's still super difficult and perhaps you won't get it because it's asking too much. But it's a different approach where you don't try to tackle the 100 meter span, you try to tackle something that was done and it may be like, wow. And actually the result of the last day is a pillow this size that you bring in and it's just dripping water, but it's dripping clean water. So just think about it because it can be like, and you are at a position where you can, don't solve it, but you're at a position where you can say something cool about it because you seem to be articulate.
Yeah, I think
so. Choose a part.
The other thing I like to add on when you guys focus on the building, I think at the moment you've been only talking about the macro scale of it. And then the really micro scale, if you jump straight into the material or the pillow, I think you have to, there is a space in between them, so that the mesoscale of the building is still kind of not so clear. And I think that will give you, the answers to how this can actually support or get supported. Because one thing is to achieve the span. One thing is to find material that can cover all this. But you have to make sure that all that area, massive amounts of area, can be also supported. And maybe there is something that they can introduce there, either exploring the material or thinking in a different scale for the air ducts or something else. But
it's another overlaying on the operations that are happening in that space. Then gives you that extra scale, as you're saying. So then you say, well, do I need this one massive, uninterrupted area? Actually, there's some operations that produce that intermediate grid system or whatever that allows you those opportunities to come and touch down. So that's a really good idea.
So perhaps you could talk to somebody that does glass houses, show this and see if this person says, hang on a second, what we would like is answers on blah blah. Then you do the next. And we tell you, this makes sense or it doesn't. Whatever, like.
One comment. If you go back a couple of slides, one where we can see the shape change between the two states. Right towards the end. No, the one where you had the two configurations. Further down. That one. Okay. This one you could see it change shape.
Then
never mind. What I'm saying is, what is still missing? And you may have it, the information, but you haven't shown it to me. Is you need to really be clear that the change of shape is actually beneficial, and by how much? Because if you bear in mind all the comments made on the structural problems, whatever not, this is adding an extra layer of complexity, and you need to be convinced. You need to convince the outside world that extra layer of complexity is going to produce something. So if the difference in production of tomatoes is 100 kilos over 2,000 tons a year, I would say, well, forget it. You know.
Yeah.
So you need to show
Yeah, like overall
quantitatively as much as possible.
Yeah.
That when you go from one shape to another, okay, according to the wind direction, no, you actually do have a benefit. Because if you take a shape which is intermediate between the two, is that good enough as a static shape as opposed to a dynamic shape? That's my question.
Yeah.
Okay, yes.
Run comparative analysis.
Yeah.
Thank you.
Hello everyone. It's Mert and my teammate Maritza. We are remarks and we are going to present bioclimatic facade design for towers. Our ambition is in order to respond to rapid growth of urban population, we are aiming to improve the current farming production system by designing an attachable secondary bioclimatic facade for towers, which will improve the living quality as well as creating a suitable environment for plant growth. So, especially after Industrial Revolution, immigration to the cities rapidly grows and it results with a rapid urbanization and loss of arable lands. Due to this, we focused on Shanghai. And it results us to ask question to us, how can bioclimatic design help us to improve natural ventilation inefficiencies and applying a vertical farming on towers?
The issue is that by 2050, the 70% of urban population is going to increase in the main cities, as you can see the density map, which shows Shanghai, and by 2030 also the is going to do food production is going to increase just 35%. So that is the lag that we would like to resolve by creating a new cultival facade in existing high buildings. Shanghai is the case scenario for our research. Historically growth, as you can see, by 2016, local production, food production has decreased and exported food has increased. And also the arable land has decreased in 10 years and in the opposite to the building land, which has increased. Also to understand the environmental parameters in Shanghai, we noticed that the humidity, relative humidity, is very high. Overall, the year is around over 80% of humidity. And because we want also to focus on plants' growth, we analyze some kind of crop species. We analyze the sunlight demand, energy demand, maximum temperature, and we wanted to relate that with radiation and wind parameters seasonally. Also, we analyzed which orientations could be cultivated our plants based on the the facades and also the hours of daylight that we have. Analyzing the plant growth systems, we focus in aeroponic because it's help us to decrease the load in the structure. Also, there is a rapid growth for plants, and also in order to collect water, we are thinking to do more research in kind of materials like MOF, which it can work like while it's night, the humid air is absorbed, and in daylight they evaporated the water, and we can collect it in a condenser. Another question that we ask ourselves is how we are going to collect the lighting artificial lighting that we will need while some months we are going to need. So we focus in photovoltaic glass is new material right now that in order to don't hide the views for the facades, we are exploring how much energy can we get it from this kind of material. And also, based on the exploration of kind of structures historically by Castle Kant, we focus in the steel system, exterior diagonal tube, and our building bases the height of 450. We analyze the wind behavior on this tower, the full tower, and also we conclude that the wind profile is relative, and in the worst case scenario, we analyze when the maximum velocity is 50 meters per second onto our tower, and that's are the results. That's our research question.
So we start. So vertical farming on towers brings us several problems, such as additional exerted load on structure, and we try to combine all of the solutions by designing a bioclimatic panel. We start our experiments by analyzing our default tower structure and how it is behaving under the conditions of the maximum wind load applied happened on Shanghai before. And then we test additional structural patterns that can be possible to create our bioclimatic facade structure. And we decide on continuity quadrangular structure due to its less material usage. Even the displacement is a bit larger than the other structures. So a quadrangular pattern creates our penalization logic, which is affected directly from the wind pressure occurred on the surface and the structure of the tower. So what we try to do is to minimize the amount of panel members and minimize the panel areas, at the same time minimizing the deflection on the structure. So we think the penalization at the same time as the structure itself, and by doing this we try to equalize the distribution of pressure on per panel. So our panel is, since we got two different aims, which are increasing the air ventilation inside of the tower and providing us a suitable environment for plant growth, our panel consists of two compartments, which are aeroponic compartment and tower ventilation compartment, and and they are having some different mechanisms to behave, changing external factors. So our tower ventilation compartment workflow is, so air circulation is based on the pressure difference. And what we are trying to achieve here is to keep the pressure difference in between the buffer zone and the inside of the tower constantly, so that we can achieve a continuous air circulation inside. And since the air velocity is directly related by the pressure, by changing the depth of the buffer zone, we are aiming to control the pressure difference. While our aeroponics compartment is controlling the volume of air getting inside in order to control the temperature and the humidity that is produced by the plants. And those parameters are depending on the plant's requirements. So while developing our form, we study on the aerodynamics of the aerodynamics, and we use Coanda effect while designing our panel. So Coanda effect is basically using the curvature of the surfaces to lead the air. And by doing that, we are trying to push the air to the panels, like panels are helping each other to take air, basically. And by different rotations, by different mechanisms that are changing according to wind direction, we are controlling the air gates to take the maximum effect of ventilation.
Another quantum effect experiment that we did is based on each compartment itself. How can we control the rotation flow to ventilate our compartments? And
we also have another algorithm to decrease the amount of direct sunlight that will create that will prevent the overheating problem in the aeroponics, which will create a not suitable environment for plants. So while doing that, we analyze the adjacency of panels, and we try to limit the extrusion difference between adjacent panels. We try to minimize it by maximizing the self-shading. And we minimize the extrusion difference because when the panels are extruded in a different amount, it is affecting the air circulation in a bad way. And we observe that if the amount is like up to 40%, we can still have an air ventilation inside of the aeroponic compartment and the tower ventilation compartment as well. But if it is exceed to 60%, we will lose our ventilation effect. So due to this, we limit. And according to the solar radiation analysis, the direct sunlight hours per panel take, we assign which crops should be produced in each panel. And we take crop parameters into consideration while doing that. And our harvesting mechanism was another challenge for us because harvesting in like 500 meter above is a bit difficult architectural solution. So we basically offer an elevator structure, automated elevator structure that will be just beneath all the panels, and we also have a rotating mechanism for the aeroponics compartment, which they can collect it. And for cost analysis, we investigate how our panels are changing the air ventilation inside. We tried with different panel sizes, and we observe that the less width of the panels are, if the width is getting less, it's affecting the air ventilation in a bad way. And we also measure how the different wind speeds affects the air circulation, and we observe like we can directly implement a different the effects of different wind speeds inside of the tower's air circulation.
Also, this one analysis based also in the wind is the control the buffers on depth, which the results, as you can see, the most optimum is the last one. And also control in order the direction of the wind if it's coming perpendicular on in lateral sense. How can we control this airflow in the living zones? Well, another experiment, we didn't explain, but it's like the extrusion panels, how it behaves. Yes, but we didn't. And the extrusion depth, how it's going to be the control, also the wind regarding to the neighbors' panels. So, in some sense. So, MR commission,
sorry because we didn't offer any final design for this. We are in a stage in the middle right now. But for Remark Ambition, we want to answer 3 questions. How can we integrate humans with nature in a high-density vertical system? How can architecture help to change our consumer society to productive society? And how can the form of the building plays a role on reducing the energy consumption and environmental pollution?
Thank you for
Thanks.
Well, thank you very much. Really challenging project, I think. I think the first thing well, could you bring up the image that's almost showing the module? One of those will do, actually. I think a really valuable diagram or piece of information would be to sort of show, I mean, what I would call the sort of structural build-up, but not structural engineering, so I'll probably call it that. But in terms of how, because it's a complicated system here. There's a mechanical system, there's the secondary facade elements, there's the primary support for the actual building itself, and then there's the primary support for the facade system. So I think that'd be really, really valuable just to show that as a build-up. That's how we tend to do that ourselves in all our projects. Is sort of as an exploded thing or a phase thing, showing the gradual. Especially for something as complex as it is, it's hard to necessarily read what is, equipment, what is mechanical, what is. So I would definitely recommend that. And that probably leads to my next question is, perhaps you could explain how you see that working out in terms of what's supporting what is primary system, what is the existing structure, what is this new curtain warning intervention. So maybe just walk us through that, right? That's my question.
So we keep
This one.
So we based on we keep the existing towers. We think the existing tower structure is. We want to add our additional structure to the structural nodes of the existing tower structure, and so the columns are generally 5 meters above from each other. So our panelization logic, which determines our structure is based on the tower structure itself. So whatever the algorithm results are, the panel's corners are always matching with the tower structural nodes.
Okay.
So that we can connect them directly with perpendicular beams.
We understand number things, just you need to show it as a drawing.
Yeah. Well, also, I think that's, so is each panel acting in complete isolation?
Yeah.
So they're actually just hung on and hanging off them. So again, I think there's 2 things there. We could just show that we've done the feasibility of that. One is that the existing building has the capacity to be able to take that either additional load, either by taking the existing facade system off and then replacing. The other thing, we showed some structural analysis of impressions of the entire building. I think again, just drilling on thing. Sorry?
There is a scale issue, I think.
Yeah.
Oh yeah.
Well, I think again, drilling down into the global definition of the entire building, whatever these numbers are, through to the local definition that the individual panels will need to take. And so again, I think in any system like this, unless it's part of the external exoskeleton that's actually forming part of the primary structure, then your facade system should be designed to be completely isolated from any of those global deformations, such that you can capture those, they can move relative to each other. So I think just capturing some of that logic, this is modular, they're coming in, they need to be hung off the building, they need to be able to, have those tolerances, they move in isolation. I think a little bit of detail around that shows a little bit. Again, it's not with the
absolute detail that show that you've thought about the feasibility of this as a system.
Yeah, I think what will also be good is to maybe be clear about the scale that we're using to represent all your ideas. Because when I first saw this slide, I was like, oh my god, the towers is so much. But yeah, you think, you know, like, yeah, when you read the numbers, like 3.2 meters is not that much in comparison to 450 meters. Oh, but then there's no relationship between the actual number and what you're measuring to. And that obviously will help. But if you go farther in your presentation, when you show the diagram with all the different sun hours per panel, the previous one? Or this one? Oh, yes. Again, I wonder if that's actually, the colors are actually matching what they are supposed to be matching, or you just randomly assign them. Like, I wonder why a 6-hour direct sunlight panel is right below a 5-hour one. You know, I can't really see why they are different based on this diagram. So maybe you have to explain a bit better that. And then moving into the panel. If you're thinking the panel as a completely isolated study, and you're not then going to talk about, you know, how they work as or how they inform the overall shape of the building, at least you have to address how they communicate between them. I know you already showed kind of a diagram having them operating on the same facade, but how do they address a corner in the building? You know, what happened in a curve, you know, shape, in a curvy tower? You know, will they still work? You know, they don't have to work necessarily, okay, unless you actually want them to work. But what I'm saying is that you have to be explicit about how they work as across the scales. You know, because if it's really a system, then it should at least work, you know, across the scales.
Yeah.
At least for a rectangular tower, I think. And then going back to your point in explaining how the system worked, you know, so it kind of had this exploded axonometric view of the system where you can point to, okay, well, this is how the facade component works, and then this is how the shelving works, and the mechanism behind it, and then this is how the harvesting, you know, mechanism work. Again, they operate at different scales, right? So the harvesting, I assume, it will operate along the height of the building, and then the other shelving may respond directly to the floor where it's attached to. You know, is it, or is it not? Or if it's completely attached to the building, then you need an external circulation area that comes behind, or not. You know, so I think being clear about these things will certainly help your representation of the system understanding.
Go to the next view. You have the 3D element.
This one or?
No, the next one.
This one.
Because you are MX, you still have some more to develop it. I mean, one aspect which I think puts your project at risk is the fact that it's completely detached from the interior. Somebody may come and tell you, yeah, the numbers don't stack up, the cost of the elevator, blah, 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 is higher than if it has a mount to get out of the lattices. And then, what do you say? You don't I think the fact that the plants themselves, they are not part of anything that can be enjoyed, utilized, harvested from the inside, is actually making this completely supposedly holistically functioning system that it shouldn't be. Because you want to hang yourselves from as many points as possible, and one of them would be where actually you have this hanging garden, whatever it is, that can be accessed from the interior, so trays, something, whatever it is. I think that the carousel little thingy that gets harvested automatically and completely externally is a problem.
or somehow the fact that this is just not interacting with the inside at all. And I would change, if you had 10 days, I wouldn't, but because you had until January, you would have to look at these ideas of, you know, what I'm designing garden.
Otherwise, it's like,
what happens if you don't make the money?
And providing some more connectivity between it rather than just being a wrap around the building. I think that could, again, provide some additional benefits and justifies it as an intervention more. And so that could be something. How do you celebrate it internally? You talked a little bit about the photovoltaic glass in terms of being semi-translucent. So even what does it feel like to be inside these spaces now? You know, almost again contrasting before and after.
So the entire electrical system just doesn't. It's just completely alien. It looks like a. Because it's like. It doesn't.
Maybe. At the moment, I think you try too hard to solve all the problems in one time. Yeah. And you know, now that you're going to jump in scale, to architectural scale, you have the potential in addressing the problem in a different way, where some panels can address part of the problem, some other panels can address another.
Okay.
Some other panels don't have to address any of this. You know? And may focus on something else, being just purely transparent.
Yeah.
You know, you can play around with this and then maybe take it apart and then think again in how you put everything together again. You know, but you don't have to solve absolutely all the problems in one single time.
Okay.
I think one of the feeling one gets is that this is a kind of autonomous super robot which doesn't want to have humans. Interfering and cook.
Thank you.
Is to develop an alternative material system for sprawling settlements in limited geographical conditions. So to give a global to a background in a global context, this is a world map which shows the urban growth pattern of the megacities in the world, which is due to population growth and migration. And the blue circles depict the increase in population. One of the major impact of this growth has been the development of informal settlements in these cities. So the pink rectangles show the percentage of urban slum populations in these cities. We chose Rio as our site because it's one of the mega cities, and it has informal settlements called favelas, which is common to Brazil. And there are thousands of favelas which are spread across the city, which are mostly located at the foothills due to economic reasons.
Rio has a tropical savanna climate with 80% humidity and an average of 180 outside sunshine hours per month, and about 50 degrees minimum and 30 degrees maximum temperature. One of the most dense favelas of Rio is Restinha, with population density which can be compared with Mexico City and Johannesburg, and obviously population grows over the years.
Also, it is located at a valley.
Due to its location on the steep slopes and vicinity to the city, it cannot be expanded horizontal direction, but it can be accommodated to the increasing population in vertical direction. In terms of growth pattern of dwellings, which depends on family growth, it extends vertically approximately every 25 years. In terms of growth pattern of dwelling, which depends on family growth, it extends each floor becomes each floor of dwellings change its purpose.
from residential to commercial. Also, each dwelling consists of different spaces, depends on the owner's choice. Currently, all structural elements such as beams, walls, columns are made of reinforced concrete and bricks, which are provided by government. To summarize, these dwellings have three key characteristics such as vertical expansion, modulation, and personalization.
Sorry about the title. To conclude, the major concerns that we have with these dwelling system is the material performance, that is the material which results in 5% of carbon dioxide emissions and 2% of global energy consumption. Secondly, since they are self-built, they have structural non-uniformity, and the fabrication process, because it takes around 2 months to fabricate one floor, and about 30% of the dwellers' income goes for the fabrication. So what we propose is to provide an alternative material which can have topologically optimized structure and can be automated, can have automated fabrication. So our research question is, through these provision, can we address an architectural system which can address the incremental nature of 100-year lifespan, accommodating the population increase while adapting to the social and environmental conditions. So we try to look at the alternative to cements which are naturally occurring, and based on their lifespan, economic gain and environmental impact, we selected volcanic ash, which is also locally available here for the like volcanic ash is globally available. Sorry, 5% of the land around the earth is covered with volcanic ash. In case of Rio, it can be accessed from the volcanic ash deposit, which is located at 200 kilometers. To give you a brief of the methodology, we want to first study the material properties through some physical experiments, which will inform our design development, which would be a component system, which will have structural and non-structural behavior. And then we'll digitally optimize the structure and we'll evaluate it further. In terms of mechanical properties of the material, we are studying the compressive strength with the relationship to the percentage replacement of cement with volcanic ash, which we realize start to decrease as it goes from 10% to 50%. And for the tension, we are using locally available plastic fibers and natural fibers. We want to experiment with different percentages and understand the relationship of deformation and load with it. And also we are considering the weight, which start to decrease with the increase in percentage of cement replacement with volcanic ash. For fabrication techniques, we try to narrow down the fabrication techniques based on the material. And as it turned out that mold production and slip forming lacks in the geometric freedom, and since our system has the requirement of expansion, so they don't want to be, they don't need to be rigid. So, and secondly, for layer extrusion, it requires formwork pressure, which is why we had to opt that out too. And we chose fabric form casting, which will provide us control variation and precision with robots. So for proposed fabrication technique, we are proposing 2 stationary robots which will have 6 axis of rotation and a 4-meter radius of reach. Also, the sleeves can be adjustable as per the position of the robot.
For our methodology for design, it will begin from physically analyzed deflection and digital optimization based on environmental and structural performance, and also our goal to decrease the amount of material which is being used. This tool will inform our further physical experiments using the robotic arms. Component geometry depends on fabrication process and allows variations in terms of thickness, size, and curvature. For architectural feature system will consist of a dome component on the top, which responds to expansion, sunscreens, and streamline components, which responds to environmental conditions, and wall screens. Also, we are exploring the possibility of assembly, where we are exploring landings, curvature and angles, and orientation with respect to each other. And also, we are exploring the joinery system. Here are the precedents of existing structures, which are made of fabric form casting also. Now we are on the stage of our design development, and we are working on non-structural elements such as facades and interior structures. That's it. Thank you.
Thank you for the presentation. I think it's quite interesting. I'm just thinking of the fact that you guys are exploring the volcanic ash, and being something that is so particular in its composition, its color, and the texture. I wonder if you are interested in exploring that side of the material properties. At the moment, I can only see all your diagrams and renderings are white. They look a bit plastic to me, or plastery. So I wonder if there is a potential here to actually explore the qualities of the material composition you are exploring.
Not at this stage. We haven't thought about the texture, but
actually, it looks like cement, a grayish color. So for
So
texture,
it has no
variation.
So that's why we
So the primary elements that you're creating through this sort of fabric formwork, so that's a sort of curved wall, it's a sort of facade, is it? I didn't catch how much. Well, so what are the design parameters that you're playing with there in terms of the? I suppose there's the sort of structural requirement for just to stand in isolation work as an element, but also the perforations. Is that something that you've been playing with? Presumably in design development, those are going to be the parameters you're.
Yeah, because of humidity in this region, we need to provide close ventilation and also sunscreens because of the sunlight all over the day. So we need to play with form of component in that case.
Okay. And again, I think there's a possibility here to, I suppose, make explicit the construction methodology that this is something which needs to be sort of, I would say, it would speak very strongly if it was something that can be done with just labour in situ. And again, I do like your idea of using the fabric as a formwork, because that's something which can be low skill level and still creating incredibly expressive forms. So I think that's something that again should be sort of celebrated in terms of the how that can actually be done. So again, big fan of robots, but actually, some of the experimentation can be done with robots to be able to very easily calibrate and control, but actually mapping that across to, in real terms, I presume you're not proposing to have, well, maybe you are, I don't know, but is a robot going to be on site doing this in situ?
What we propose is a fabrication in factory and assembly on site, because people are already self-building it, so we just propose to assemble it.
Right, okay. Okay.
So it will be pre-found.
Why the fabric then? Because to me the fabric would suggest the fact that it can be done more locally. The minute, I don't know, the minute you do it all robotically far away, it becomes a bit like you might as well do whatever.
Well, then again, there's a possibility of standardization, as you would almost say you get actually greater benefits of having a standard mold and then just cast it. So again, I think it's worth mapping that whole process out to sort of work out, you're playing to the strengths the fabrication process and the material.
In terms of the system, are you imagining this to be structural as well?
So structural and non-structural.
And so I suppose it will also need to deal with the enclosure of whatever you're.
Yeah, that's why it was expanding images. So it has to grow. So that's why we are proposing an add-on.
Or the phasing of the land.
Oh, is it?
Yeah.
Right.
Yeah.
And it will have to also deal with weather.
Yes. So that.
So are you thinking this working in conjunction in a different system will provide a weather barrier, or
It's a screen.
it will work just as a screen and then as a primary structure? You will have to.
Due to different dimensions of components, we can provide cross ventilation into the building. So we're directing airflow into the interior. So we to increase the level of cross ventilation in the buildings.
So the building will remain open?
Yeah.
Sorry, can you step back one? Because, yeah, it's not entirely clear how we go from this to the next one. Suddenly there's sort of wide beams that become panels, and it's not entirely sure how that transition is made. I'm not saying it's something you need to show, because here we see some kind of system, basic element, but then what we saw in the next slide is not that element. So,
and I think it does, I mean, the question there was quite pertinent, because it speaks to me as a modular sort of facade system. So if it is going to be a primary system as well, that, you know, the load path analysis and everything, just demonstrating that the app actually can. And that's been thought about. I'm not expecting it to be completely resolved, but it's been thought about.
Absolutely, that's right.
Yeah. Well, I mean, especially these elements will be supporting the slabs for the structures. So obviously there will be.
It's meant to be structural.
Yes.
And then I would have a bit of concern about the connections here as well, because actually. One of the benefits of a concrete frame system is you can get monolithic connectivity through your connections. So actually if you're doing it as prefab and bringing them onto sites, detailing that connection so that actually either it's working to not transfer the moment or it is, and then detailing that connection will actually be very important if it's a prefabricated modular primary system. If it's just a prefabricated facade system, and that's less of an issue. But yeah, thinking about a few of those might steer you in a different, or focus your direction or steer in a slightly different direction in terms of the fabrication and the construction approach.
You have to think strategically now what to direct your efforts into, because you have to provide more evidence that the stuff works. It can be the loads, the paths of the loads that they come down. It can be the detailing, whatever. So just think, what are you better at? Forget about fabricating little thingies and then next time you just bring here lots of models. Or if you're better at simulations, and we just need to see, we just need to see more stuff, more intensity. I mean, you have months, no?
Months, yeah. And again, if this is the sort of primary sort of multi-story, future multi-story building, then you're going to have to tackle the reinforcement issue against concrete. And that could actually be tackled in a quite elegant way. So whereas fabric, well, the fabric formwork then becomes permanent. Because I don't know, there's options there, but I think you definitely need to tackle that if it's taking significant structural errors.
Well, you can also set up the rebar, through with whatever frame you're using.
Okay, thank you.
And Miguel. And so the ambition for our project is to sort of design a ecological system and construction process for earthquake-prone residential settlements and landscapes. So really our goal is to fabricate a composite material system that can sort of aggregate and deploy as habitable infrastructure and is produced by readily available materials in Kathmandu, Nepal. So really we want to focus on the relationships between material resonance, earthquake-resistant structures, and fabrication processes. So you may know in 2015 Kathmandu was hit by an earthquake and it displaced many, many people. And 3 years later, we all had a chance to go, and they're still rebuilding. And that's probably due to lack of funding and lack of proper materials that they have available to them. So what you see in blue is where most of the buildings were affected. About 1,200 buildings were affected, and most of them were made of Adobe construction. And unfortunately, Adobe construction actually contributes to over 80% of the overall pollution, and it performs poorly in earthquake-prone areas. And that is because?
So as the majority of the buildings were made out of Adobe in the area, so we look at how Adobe fails, and it's mainly because of its high mass and extreme brittleness that it fails in an earthquake situation. So we propose to replace the Adobe with a biomaterial composite, which in the case of our study is mycelium, and which is the sort of like the vegetative interwoven filamentous part of the mushroom which forms before the mushroom sprouts, and this can be combined with a variety of natural substrates to produce different properties, resulting in a natural polymeric composite fibrous material. And so we looked at some of the existing research which has been done on mycelium, and we see that like its mechanical and structural properties are similar to that of Adobe, but with really low density and weight, which is beneficial for our cause. And so mycelium is a biodegradable material, easy to produce. So the biodegradability of the material was important in this case because the Adobe construction, the debris that were formed from it after the earthquake resulted in a high, further pollution of the environment. And so the mycelium material would be easy to produce from local resources, and it's a low cost and minimal pollution material with a high strength to weight ratio. And so we look at precedents of biomaterials in architecture, and which have been like flexible formwork, block masonry construction, and 3D printed molds for the material to grow in. Out of these, we are looking at flexible formwork and making a sort of mold from the flexible formwork for the mycelium to grow in, because block construction is not favorable for earthquake situations. So here our research question becomes that can a composite mycelium material be developed to achieve earthquake resilient behavior through manipulation of material properties and geometric configurations while reducing pollution due to vernacular Adobe construction methods in Kathmandu, Nepal?
So moving on to the experimentation, we have computational experiments and physical experiments running simultaneously. We chose to start with our physical experiments to really understand how this material works, and really focusing on sort of the natural growing process, from choosing our substrate to sort of finishing, and how this thing grows and how we can control the moisture and light. So we kind of constructed an environment here at EmTech where we were focusing on how we can waterproof and sort of protect from sun, because we need mycelium to grow in cool and drier environments. So we set up 4 experiments using 4 different types of substrates in this sort of block formwork. We found that oat and jute actually didn't work so well because we were probably lacking a clean environment at the time, and we noticed that oat paste is kind of too moist for growing mycelium. So we focused our further research in looking at the composites with aspen and hemp. This is like what the substrate kind of looks like in the beginning, day 1, and this is what we can sort of achieve by day 20. So what we noticed is that the harder the substrate, the more dense the resulting composite is. So I mean, you guys kind of felt it. This one here is aspen, and this one is hemp.
In the aspen sample, you can actually tell that it has a slightly wooded properties to it, and the hemp is slightly more spongy.
Yes, exactly. And we also noticed that in our formwork, we have to sort of make it of a non-organic or non-fiber system, because when we're peeling off the block formwork, it actually sticks to the mycelium. So anything like plastic, acrylic, that was working better. And obviously we need to improve sort of our sterilization of the environment in order to get this going. So moving into our computational experiments, we wanted to focus on the relationships between sort of the traditional vernacular house, how we can sort of optimize for earthquake resistance, and sort of understand how we can create this formwork geometry in order to propose a new 3 to 4 story building.
So now we're going to the study of earthquakes and how they affect structures. This is just a small refreshment of terms, of terminology that we'll be using from now on. So essentially, when approaching earthquakes, there are 3 main techniques. Either you make a structure extremely stiff, which costs money. Either you do a dynamic approach, in which we have things like tuned mass damping, like in the Type A101 building, in which you essentially mitigate the effects of the earthquake through an active system, also expensive, and usually for higher structures. And the final one is by increasing flexibility and adapting to the waves of the earthquake and allowing the structure to deflect under the conditions. So we started branching from trees in nature. As you can remember, trees during an earthquake tend not to fall, not to be affected. So we studied the effect, we did a quick run through branching and how the modal frequencies of each individual tend to be lowered when branching is increased. Individual 5 is the one here where branching is. We'd also define a range, when an earthquake occurs, waves, the destructive waves of the earthquake are within the range of 1 to 6 hertz. And so we want to bring our structure to be there in order for it to oscillate and dissipate energy through branching, which is essentially what trees do, and that's the essence of our project. And so this is a case study in which we start to manipulate either the thickness of the branches or the length of the branches, and for individuals A to B, B being the last one, we can start to see how we can lower the frequencies of our structures. So from this we learn that energy dissipation occurs through the oscillation of elements. So we want various elements to be active in the structure and move during the seismic event in order to dissipate energy efficiently.
So we start by a form-finding experiment where we take the Newar section and the sort of spatial relationships where they're more private on the ground floor and more public on the top floor, and we kind of assign values. We assign values to those relationships, where the more private the space, higher sort of the repeller, so that we can sort of let these agents avoid those spaces. And then also taking from our branching principles, trying to add branches or adding a system in addition to this sort of sectional relationship, so that we can get our agents to sort of have moments of separation and moments of these branches. So we run the agents, and we took the behavior sort of inspired by the mycelium growth at the molecular level, but we kind of focus on sort of manipulating the growth rate and sort of the attraction forces, like I mentioned, for the earthquake branching principles. Then we look at the critical nodes. We see where these agent trails sort of are more dense, and we start triangulating between them to sort of create our structure. And so this was, like I said, a form-finding experiment, and we were able to get a variety of 3 to 4 story building proposals. So what we can do, going back to our earthquake branching principles, is what we can change the length, we can change the diameter of these beams, and we can change the nodal mass of where these critical connection points are.
So in like our next step will be to set up a GA with all these parameters that we're using. We are not there yet, but we're doing this. And we'll have a fitness criteria in which we will want to have our modal frequencies occur in the range we want, minimize self-weight displacement, and minimize material usage. So structurally, that's what we're looking at right now. These are our examples of what we did. If we start with a branching system like the one above, we know that this is not a feasible geometry for a building. But if we can achieve something like the last example, in which we have, imagine, towers oscillating within the system separately, then we can achieve this branching behavior. This is proven through experimentation.
We did the structural analysis on these forms, and we noticed that an open branching system is more desirable over a closed one due to sort of overall lower displacement and modal frequencies. The displacement values here are actually scaled up by 5%, just so that you guys have a visualization of how this thing moves. So they're not absolute values, but we understand that at least by this experimentation, we know that the modal frequencies were out of range. So
this was our first run with 4 geometries we chose from our agent iterations. As we can see, they are starting to come to range, but they're still beyond the 1 to 6 hertz earthquake range. So we do one more iteration. We subdivided the mesh even further, and we started to achieve some branching elements. At this point, the architectural consideration is not clear. We envision that maybe they can be separate towers or just sole elements meant to dissipate energy.
But the good thing in this example is that you can clearly see that the individual towers that are sticking out are dissipating all the energy, which leads to the rest of the structure not oscillating during an earthquake branch.
So that iteration proved to be way more close to the range we want to achieve. So that's through our experimentation, we've managed to achieve a closer result to what we want.
So sort of how do we fabricate this now, right? We have this crazy form, so we wanted to go back into the physical experiments and focus on our flexible formwork.
So for the physical prototyping, we took a part of this geometry which we can sort of, which can be modified and replicated all over the system. And so the aim was to develop a sort of construction technique derived from modular parts, by modulating these parameters such as the beam length, the radius of the discs, and the distance between the node and the beam, to be for it to be able to create the entire mesh system that you see here, and for it to be a sort of non-specialized, easy to create system by a non-specialized labor. And in the beginning of this, we're just starting to create this prototype, that one, and we realized that there are some problems which we have now, that once we are bringing the ropes in tension and we start to wrap the flexible fabric around it, it drastically reduces the radius of the beam that we have designed it to be. And so we need to maybe add more discs or create more tension, and the most critical drawback of this is right now that the precision of the system, because this geometry needs to be highly precisely fabricated for it to do what it's meant to do. So for that, we are kind of looking at some sort of a guiding tool which can be created.
So what have
go. As a final note, we want this to be labor intensive.
Oh yes.
This system to require a lot of man hours to be constructed in order to generate employment within the calendar region, which is one of our...
Yeah, because it goes back. I mean, we have over...
That's why we're keeping it low tech.
Because we have people sitting there. We need to make it work. So what have we accomplished? We sort of established our logic for our form-finding experiments, which need to be refined, obviously. And also, we've established sort of how that loops into our structural system to increase earthquake resistance. And we sort of have sort of the limitations of this sort of fabrication process. So it kind of leads us to the question for the MArch phase. Can we sort of facilitate the fabrication process by developing an interactive application that increases precision and help visualize complex geometries? So thank you.
I have a really good presentation. It's fun. I have a question on the mycelium. By the end of the presentation, I was a bit lost about where in the mix was the mycelium. Is it supposed to be applied afterwards, or?
It's
inside.
So we make the former, then we use it as a mold to fill the mycelium in. And
so it's actually part of the mix.
This is how we're just preparing the mix.
Now it makes sense again. And I think, it's really interesting. At the moment, it feels like you guys are focusing on the, let's say, the straight elements of this lattice. But on the diagrams you were drawing, the more complex areas of the systems are in nodes, or appear to be in nodes. So if you want to focus on the fabrication method for this, I think the nodes will be kind of a really important area to focus.
Yes, of course.
The development. And again, I think it's also a matter of thinking how are you guys going to, or thinking to apply this. When you talk about the tower, I was thinking, are you imagining an actual tower, or just a tower?
We might have failed to mention this. Generally, the wiring architecture is based in a 4-story house. Like their spatial distribution is vertical, and so their family nucleus is organized in a vertical fashion. So generally, it's a 4-story building.
So if that's the case, then you certainly need to address the spatial qualities.
Yeah.
Yes. So at the moment, we're filling the whole volume. So what happens when you get one of these members, crossing a very important area you have open or something? Basically, you also make sure that this will allow for the space to function, for the building to function as well.
Yeah.
Also to verticals of slabs and also all other stuff that you usually put in buildings.
All the architectural considerations.
But really interesting.
Building on your point of the nodes, I think actually it would be worth considering that, if you say prototyping that, but then almost you might find where are you going to make the connection, and it may not be, especially in terms of as you know, as you highlighted, the stiffness of the system is going to drive the natural frequency of it, and so the stiffness of the nodes is going to be, again, that continuity is going to be paramount. So you might actually be able to do a quite clever study on where is the point to do the break. It might not be at the node. It might be at the midpoint along the line. It might be probably 3/4 along or somewhere. So I think that's a study that's really worth looking at. Also, obviously the stiffness, capturing the stiffness correctly, but also as you highlighted as well, the mass and the distribution of the mass in the system. So I think, I'd certainly like to see that you've incorporated the allowance, if nothing else, for the extra mass that's going to be in the system once you've incorporated in the really annoying things like horizontal slabs.
Yes.
A whole load more mass in the system. So I think you need to make sure you've got that allowance. But equally then, making sure you're accommodating, okay, you've got the primary system is what's got the continuity. So I think you'll find something else which was quite interesting, that you had a sort of taller tower that's working as an oscillating thing to dampen the system. So you might have slightly different construction tolerances or movement tolerances in different parts of the system of building. I think highlighting that and demonstrating you, because that actually could drive the different types of construction and the different types of uses in the space. You're probably not going to want to do some plumbing right up to the top of that tower. Really flexible pipes, maybe other parts. I mean, that could be almost providing some sort of dialogue between the structural solution and the spatial usage as well. Not to mention the construction tolerances. Really weird stuff.
It's very strange. I've got one question on that. because which relates to some extent to some. I mean, what I would be interested to know, apart from obviously, logically you want to try to grow your structure as a continuum, if you like, without discontinuities, but on the other end, discontinuities may be helpful for other reasons. My question is a very simple one, which just crossed my mind now. If you take the two samples, the softer one is the one with hemp. The stiffer one is the one with
aspen.
My question is, okay, are these two, if you take two aspen, a bit more rigid, are they joinable by any technique?
In
other words, can you make a mechanical joint between two bits made of that stuff?
Can you grow one?
I mean, we
generally it will be a continuously grown structure.
No, I know, but at the same time, okay.
Like a gradient between aspen and like a gradient between like an aspen.
If I got two bits coming out, okay, can I join them together mechanically? And is that joint going to have any performance?
Right.
I'm just curious because you mentioned the Japanese pagodas. And there, everything is coming out of the joints, and the joints are made in wood.
Right.
Okay, and yet they are still there. So after many earthquakes. So what I'm saying is that there is, don't forget the fact that the joint may be beneficial. Okay, in more than one way. Partly to solve problems, geometrical problem, complexity, whatever not. Partly because they may contribute actually to some of the performance level anyway. But out of interest, you know, it would be really quite interesting to know if these things can be joined. And what is the load bearing capacity of the joint to make this stuff.
How do you imagine when you say it's continuous? How do you imagine that?
Like so...
growing something.
Is it something, I mean, you could look at the way concrete is cast, for example, in fabrics, and there are successive lifts. And the next lift is poured when there's still possibility of a molecular bond between the previous pour and the new pour. So maybe this has to grow in a closed seal. But there's a point where you could release one at the top of the container, or
add more,
where there's sufficient stiffness. I don't know. I think that's.
It's something super interesting that you haven't checked. I remember I once tried to do a sculpture, and it actually started to work, and it surprised me is the relationship or the interaction between the textile, flexible textiles and aggregates. And because you have this thing, I don't know what it is. No, there's a thing inside. If you put, say, maybe like a tie, and you put this thing inside, it does arch to the edges, to the point that it doesn't let the load down. So you can make like a bulb on it, like a natural, I mean, if you put, imagine a tie like that, and it's like flexible, and you can put a bulb like that, and you keep putting stuff on top, it will not pull down because it arches to the sides and it brings it in. So I think there's quite a lot that you can study of how this is not aggregate, it's something, it has more cohesion than aggregate, more than sand. They actually start to breach out and create those things naturally by the way in which you put them down. And then create these things just by the flexible fabric and this thing, which is not aggregate, it's a funny thing, it's like grass. So if you put grass, just by the way it works, it will add sides, it will, the thing outside will try to pull it in, and it literally blocks the top. It's like it's like a pipe that gets clogged. So you can use the clog as a way of parsing whatever the fact. It's super easy, and you are playful enough to play with that. Because another group would be like all this, but you guys are into the nets and everything. So I think that sort of like clogging effect can be a nice way of fabricating these things in the node. And I think it will give you constraints to then go back to the model because the model looks a bit out of the blue. And it shouldn't. I think it's nice you've done it, but why not feed it back with a couple of stuff?
Okay.
Which I think,
Cool. Thank you.
Thank you very much. Please join me.